Welcome to the first keynote address at SMI 2021. And it's my great pleasure and honor to introduce our speaker today, Dr. Tom Nichols. And many of us know Tom very well, but I still give the formal introduction. And Dr. Nichols is the professor of neuroimaging statistics at the Oxford Big Data Institute. He's a statistician with a solitary focus on modeling and inference methods for brain imaging research. And Tom has a unique background with both industrial and academic experience. And he also has diverse training. He earned his PhD in statistics at Carnegie Mellon University with cross-training in cognitive neuroscience. After joining the faculty at the Department of Biostatistics at the University of Michigan, Tom was the director of modeling and genetics at GlaxoSmithKline's Clinical Imaging Center at London, where he developed methods for FMI clinical trials and imaging genetic studies. In 2009, Tom received the Willie Young Investigator Award by the Organization for Human Brain Mapping in recognition for his contribution to statistical modeling and inference of neuroimaging data. It is really great to see a statistician receive this very high honor from OHBM. Tom is a developer of both the SPM and FSL tools, both of which are the most popular imaging analysis tools. And he's well known for bringing advanced statistical methodology to brain imaging and make it accessible to non-statisticians. So I think Tom is really a leader working in the interface between imaging, statistics, and neuroscience. And he has made significant impact in imaging statistics and also computational neuroscience. Again, it's a great honor to have Tom here to deliver the keynote talk at SMI conference. So without further ado, Tom.
Thank you. Can everyone see my screen?
Yes.
Great. Okay. Well, thank you for that warm introduction. That was it's great. As I was saying, it's unfortunate we can't all be together. I'm going to talk about two different things together. I really wanted to talk about the second one, but I felt like I sort of had to talk about the first one. But first, let me say, I really miss conferences. This is, of course, in the center, Keith Worsley, next to a student, Jonathan Taylor, and the person on the left is some nameless person who's lost to history from an Organization for Human Brain Mapping conference. But anyway, I miss Keith sorely, but I miss conferences, and I'm glad that we're at least able to do this. So the thing I'll talk about first is some work on Pearson's correlations as applied in fMRI. And as statisticians, you really kind of think like, really, we're going to talk more about correlations? Can't we get people to do something more sophisticated than correlations? But unfortunately, correlations are deeply embedded in the methodology for fMRI, and so I think that there is something that needs to be addressed there. But then I'll try to dispense with that quickly, and then get on to this other work that I've been doing with Norman Schwartzman and his group on trying to get more precise inferences on spatial location on images. So neuroscience is driven by correlation, and one of the areas that I think depends most heavily on it is what is sometimes called graph theory or graph theoretic methods as applied in neuroimaging. And in that setting, you basically create regions, or you have a single region for each voxel or surface element, and then you work out correlations between them. Now, for many of these methods, they actually will just threshold those correlations or by some way, by p-value or value somehow, and then make decisions on the characteristics of the network. So they might talk about degree, that's the number of edges that a node has, some measure of betweenness, how often a node appears on a path between other nodes, and then measures of clustering, so local efficiency. But all of these measures depend on how you get from the actual data, in this case fMRI data, to correlations and then threshold them. And so this sort of made me think carefully about this. And I think there's some things that we all know, I think, and there's some things that maybe not all users know. So we all know that, of course, with more sample size, if you compute a correlation between two random variables, the sampling variability of that shrinks. Yay. But maybe not appreciated by all or by some, of course, is that the sampling variability decreases as the n, as the true correlation coefficient rho gets away from 0. And this is approximated by this simple expression here, and that motivates the use of Fisher's transformation. So Fisher's transformation, which is the arctan arctan hyperbolic function, miraculously here for showing you for a range of different rows, 0 up through 0.95. Now we have the same standard deviation for all these, and that's really good. And so I think people have some sense of that, but I think what is not appreciated as much is that when you have serial correlation, so when the individual variables that are submitted to a correlation themselves have correlation, in this case, temporal correlation, that's going to affect the sampling distribution of the correlation coefficient as well. So here's an example where I am simulating relatively short time series, correlation length of 50. True correlation is 0.5. The details are down here if you care. And then vary the strength of the serial correlations in each one of the respective time series in X and Y. And you can see that actually they're still pretty well centered about 0.5, but there is tremendous changes in the variability, and as you can see in the skew of the distribution. So does Fisher's transformation help here? Well, yes, it does address the skew, and you get something that's a bit more symmetric, but there is still variation in the standard deviation. Even though we have a fixed number of samples, 50, we have dramatic differences in the sampling variability. So I think this is something that I think most statisticians are probably aware of, and maybe just to be aware, or maybe not, they may do not know of the various solutions for it. But what really drove me nuts is that I wasn't sure whether neuroscientists were really aware of this. And the first place that I got an inkling was a paper I read from 2005 from Marcus Reichel's group. And it just had this reference. Because individual time points in the bold signal are not independent, the degrees of freedom must be corrected according to Bartlett's theory. Now, I never actually used Bartlett's theory, and I couldn't honestly find it in the textbook that they referenced. And of course, if you do look in statistics, Bartlett's corrections are actually sort of asymptotic corrections to asymptotic confidence intervals. They're not actually specifically about correlation, for example. Then I next saw it coming up in another paper from Randy Buckner's group, and there they called it a Bartlett correction factor, and they gave a little bit more, for a few more breadcrumbs, and they said the data set, the Bartlett's correction factor is computed as the integral across time of the square of the autocorrelation function. Okay, well, we can forgive them for talking about an integral of something that's discretely sampled. But what do they exactly mean there? So do they mean summing up all the lag correlations, lag 1, lag 2, lag 3 squared? Or do they add in the 0th autocorrelation function value, which is 1? Or do we actually have to go from minus lag up to positive lags? And really all the lags? Complete lack of detail, not clear at all. And so I had a grad student, this work started when I was at the University of Warwick, Skew Afuni, who took this up and basically did a deep dive into the statistical literature and saying, well, what has been done about this? And there's been a lot that's been done, and this will be a quick review of that. So the original, the variance of the Fisher's transformation correlation values goes back to Fisher in 1917, who found that it had a variance of 1 over n minus 3. And so here is Fisher's transformation here. Bartlett actually then proposed a correction for an order 1 autoregressive time series setting. And I think he mainly assumed that the autocorrelation was similar, but you also could pose it like this. Later in 1946, he relaxed that from being for an order 1 autocorrelation coefficient to this general form here. And so we assume that's what was being referenced by Bartlett's theory, was this work from 1946. Now, that work assumes that the temporal autocorrelation, the serial autocorrelations in X and serial autocorrelations in Y are the same, and also that there is 0 cross-correlation, that this is a result that is good for you only under the null, which if you're just doing testing, that's fine. But if you actually want, accurate standard errors for any true row, then that's not so great. And so a more general result was then, and so this if these papers were trying to implement this correctly, they should definitely include the 1 for the zero lag autocorrelation function, and you have to sort of account for the fact that this result is going from minus infinity to plus. Now, there's no comment about, and I will return to, like in practice, we usually don't consider, at some point, we basically say, we don't believe that there's autocorrelation beyond a certain lag. So, of course, there are important details about when do you give up and so call that equal to 0. So more work was done on this, and that was proposed actually first by Bailey and Hammersley back in 1946 to have this sort of equation mode, and actually later, not aware of that result, Clifford Richards and Hyman gave the same result in matrix mode. So these two results are the same, and these are better, but they are still they still assume that the cross correlation is 0. So they're more accurate results, but they're still, and they actually allow for different correlation in the X, different correlation in the Y, but they are still under this null setting. I will say that this issue has been sort of, there is some awareness of this. So in the FSL toolkit for connectivity, something called FSL nets, they are aware of this problem, but they do take a very basic approach. They simply say, well, there is a common autocorrelation autoregressive order 1 autocorrelation, estimate that over all edges, over all subjects, and then do a little mini Monte-Carlo simulation to see what is the variance of the correlation or the Fisher's transform correlations in that setting. So that's reasonable, but of course he has even more assumptions, that it's assuming that it's autoregressive order 1, it's assuming that those correlations are the same everywhere. So Soroush worked really hard, and we're really excited when we ground out this result. It was sort of horrible linear algebra, but actually find that yes, you can get a result that tells you the sampling variance of Pearson's autocorrelation that accounts for the autocorrelation within X, the autocorrelation within Y, and the crossed and lagged correlation between X and Y. Not just at the 0 lag, which is our usual correlation, but for different lags. And a minor note too, that lags are not symmetric. The cross correlation is not symmetric. So a cross correlation between X and Y for a positive lag is not the same thing as a cross correlation for a negative lag. We, however, soon realized that actually we have been scooped by Roy. So actually there had been a paper in Biometrica that actually had this. I still think we have a sort of more elegant, less sort of weighty proof of it, not making asymptotic arguments, but just sort of grinding out the algebra to get to the same place. So we're a little bit disappointed in that. But there still is some questions about how would we deploy this method in practice, because these things in general have to be, you have to give up at some point. Up to what lag are you going to try to use this? After what lag are you going to assume these are 0? I'll get that to a second. Also, I guess I want to say, so what about Fisher z-scores? Well, actually, Fisher z-scores are kind of neither here nor there, because basically what matters is, what is Fisher z-score? Well, that it is for anything that you push through an arctan H, it's based on the a Taylor series or a delta rule that just says, well, take the variance of whatever you put in and multiply what by 1 minus the mean squared over over the 1 over the squared power. So this is just a property of this transformation. You can push any random variable through that, and that's going to be the correction. So if you want to make a z-score and account for these results, you're just going to take the transformation, divide by the variance times this. And of course, if you recall the classic IID result, well, that's just 1 minus the true correlation squared, and so that cancels out. And that's, of course, how Fisher derived this as the variance stabilizing transformation under the IID case. But when we don't have IID, we have correlation within X, within Y, and cross correlations between them, this is not going to work. Some people like to talk about effective degrees of freedom. Well, really, effective degrees of freedom are just nothing more than 1 over this term here. So that will be, that's basically what it's going to be. This would be the ratio of this with then, and that's what you're getting there. Okay, so how do we actually deploy this in practice? And this honestly, even if we'd found the Roy result right away, there's still the heavy lifting of figuring out, well, what will this work for finite? I mean, maybe it works with a time series of length 10,000, but nothing shorter. Well, so this was the heavy the work that Sarouche undertook, was figuring out what are we going to use for these. Now, if you look in the time series literature, there's no good theory. I would say there's various rules of thumb that say truncate your autocorrelation functions after n over a quarter, n over a fifth. A lot of people think that tapering is a good idea, and that makes sense. Tapering is when you sort of smoothly scale the values, the autocorrelation values to 0, and but that also has a parameter m, after which all the values are 0. And you find different things in literature. Actually, I think square root of n is recommended. So square root of 2n is recommended, but the FSL software actually uses root n. So this all seemed arbitrary, and if they were that arbitrary, we thought, well, why not just do this sort of seemingly sensible thing? Let's just do the usual test. There are large sample tests for each lagged autocorrelation. We're just going to do a hypothesis test, testing these are 0 at an uncorrected level, just for the first lag, second lag, and so on. And after the first non-significant test, we'll set all the rest of them 0. So it's something that we evaluated relative to everything else, and it seemed to do as well or better than any other method that we considered, and it just was practical. And we do that both for the property for the x time series and the y time series, and then for xy, we'll just use the larger k of either of these two. So that's the method that we then that's how we actually made this method. It actually depends on lags from plus or minus infinity to be practical. But the first question is, well, does this matter? So if this autocorrelation is the same, is it such a big deal that we estimate the autocorrelation separately for each pair of variables that we feed into a correlation? And it was my guess that it was, but it was we really were it really is that case. If you look voxel-wise, there is tremendous variation in the strength of autocorrelation across the brain. I don't know if there's a formal name for this, but we just found a useful way to summarize the severity of the autocorrelation by just summing up all the squares of the autocorrelation function, and that's our metric. So it's really large near the edge, and probably near blood vessels or blood-brain barriers, the boundary between CSF and gray matter. And then we considered some commonly used atlases, Yo Atlas, the Gordon Atlas, and also the Power Atlas. And the first thing you notice, if we summarize the strength of the autocorrelation, these correlations mostly, from most voxels, are relatively low. But once you average them into one of these three atlases, the strength of their autocorrelation it gets considerably stronger. So this is something you'll see. Whenever you average data up from individual voxels into a region, you basically are the independent sort of thermal noise cancels out, and you basically get a strengthened view of the physiologically induced temporal autocorrelation. So this we see time and time again. Excuse me. The other thing that we noticed is that the correlation severity of the temporal autocorrelation seemed to vary with the size of the regions of interest. And you definitely see this here. If we plot the autocorrelation length against the cube root of the voxel size, you see that there. Excuse me. And also, the reviewers asked us to think about independent component analysis time series. And it turns out if we come up with an effective way of talking about size of regions of interest of a spatial ICA map, we get a similar relationship. Now, the Power Atlas is interesting because it has all equal sized regions of interest. And so you might think there'd be no dependence there, but we did find, and I'm not sure if Benjamin Risk is attending, but he recently published a paper that noted that the severity of autocorrelation varies substantially over the brain. And in the Human Connectome Project data in particular, the data near the core of the brain, and we picked the thalamus as a region, the autocorrelation is much weaker in the center core of the brain relative to the parts that are farther away from that. So this is really serious. This is saying, yeah, sure, if I compare these two regions that are in the cortex somewhere, they have comparable temporal autocorrelation. But if I was making a correlation based on this node and this node, there's dramatically different temporal autocorrelation between those, and that needs to be accounted for. So we did ample Monte-Carlo simulations over a range of settings, evaluating the existing methods that are in the literature, as well as our method, and focusing on the bias in the variance of the sample correlation. Again, Fisher's is really kind of irrelevant here because you just slap on the delta method variance transformation. So we did it both ways. Basically, the story is the same. So I'll just focus on the variance of correlation. And you see that for null, so on the x-axis here is the true correlation between x and y at the 0 lag. And for 0 correlation, actually, all these methods are not bad. They're pretty well unbiased. But as you increase the temporal correlation for all sorts of different equal or unequal temporal autocorrelations, they get catastrophic degrees of bias in them. Whereas for our method, we basically, it's not perfect for short time series, but it's doing much better and much more stable over increasing lag 0 correlation. And for a long time series, it's doing really well. But going back, the thing that's interesting here is that some of these methods, look at one of these settings, WW. So that was white. So we actually did say, if you're going to use one of these methods, Bartlett's, Bailey, and Hammersley, whatever, and you actually have no temporal autocorrelation whatsoever, they're just as bad. They all go off the rails. And this is really perplexing to us because if the data are white and white, why would this be an issue? Well, we actually discovered this really kind of interesting thing is that the Bartlett, all these methods here depend on the product of the autocorrelation functions at a given lag. Okay, so the product of the autocorrelation at a given lag, well, how would you estimate that? I guess there should be hats here. You'd estimate that as the product of the time series at xt and xt plus 1 at some lag times that quantity at some yt and yt at some lag. But of course, you can rearrange this to look like this. And because we're under this case where, and even that there is no dependence in time, you can actually say, well, actually, what's happening here? This expectation here, this expectation here, well, that's just the correlation. And of course, this here is just a correlation just at a slightly different lag, but it's the same lag. This is still 0 differential lag between x and y. So this is saying that there's an aliasing. So whenever you have an algebraic expression that depends on the product of the autocorrelation functions for x times the autocorrelation of y for a given lag, that will be basically is algebraically equivalent to the correlation, and hence why, as these things grew, the true correlation grows, even the white case gets incredibly biased because of this aliasing here. So that's the serious problem that I think, indeed, these methods were never intended to be used under non-null, but it's interesting to think that if you actually did deploy them, you would have this serious problem. So this is null evaluations. I'll start to skim through this stuff, but basically we did lots of different simulations where we took, sorry, these weren't simulations, you're actually using real data, but where we took one time series from one individual and we correlated it with another individual, because of course in any given brain and a real human, all the different time series have lots of correlations among them. So getting null correlations is hard, but of course if you get another resting state data set from a different subject and you just say, okay, it's the same 1200 time points, kind of correlate them between subjects, you really know there should be no correlation between them. And when you do no adjustment, or any of these other adjustments, you can either get over some of these adjustments overcorrect, and of course not doing anything undercorrects. And with this XDF, we call it XDF because it isn't effective degrees of freedom, but it's accounting for the cross correlations. We get nominal p-values. Another illustration on one data set, null data set, to just show that if you just naively did the n-1 over n-1, 1 over n, or 1 over n-3 variance, and you naively created the z-scores, you would find lots of significance correlations. But again, this is between two different individuals. There's no reason why they should be correlated. And then when you do the XDF adjustment, all these come in and we get no FDR significance and the expected number of null significances. And importantly, the degree of the correction. So we found one time series that actually hardly changed at all. And that was a correlation between some region that had almost no temporal autocorrelation And as compared to a correlation between two, these are two different subjects' data, but still they're highly temporally autocorrelated, and hence they have they have great sampling variability. And so the XDF then says that needs to be corrected and changed. And so it goes from the naive approach, it's almost a z-score of 4, but after correction, it's less than 1.5. So it's doing its job. And the final thing, which is actually how this all got started, it was that when Sarush started working with me, he had actually just done projects using graph theory and computing these measures like degree and betweenness and local efficiency. And this is the thing that really sort of startled me. So if your science is all about just trying to understand how the brain works as measured by degree, betweenness, or efficiency, you will get dramatically different answers, whether you use a naive Fisher's Z transformation, which is basically like doing no transformation at all, just because it's monotonic, it's a single transformation. And if you do this correction to give you valid Z scores that actually are telling you how many standard deviations away from 0 is this measure here of connectivity. And so these are Bland-Altman plots showing you the differences for there are different ways of doing the thresholding. You can do a local sort of a fixed threshold, or you can do an FDR threshold. In the Bland-Altman between doing a naive correction versus our XDF, and you can see there's a dramatic difference between these, and that is, and that's we did for comparison. We said, well, what if you did the Hammersley one? Well, if you did the Hammersley one, that actually overcorrects, and you actually get a different relationship. But the bottom line is that these things are showing systematic differences depending on whether you appropriately compose z-scores or not, and this seems to me quite dramatic. So there's a tool for this, and I'll just give the quick takeaways. That you must always remember when working with these correlations from resting state or even task-based fMRI, that the sampling variability of Pearson's correlation depends on the autocorrelation in the one variable and the other, and the cross correlation. And there's ample evidence that for any given pair of variables you consider, you probably have different autocorrelation structure between the X and the Y, and you need to account for that. My sense is that this is underappreciated in neuroscience. I think some people are dimly aware of it, but they sort of have not taken on all these subtleties. And I will say, though, it could be that some neuroscientists are really satisfied to just make inference on R. And if that's the case, then monotonic transformation of R, which is A tan H, if that's fine, if you're not trying to make inference. The thing I struggle with is so often people say, oh, I use Fisher's Z. And so I asked, so this is a z-score that's telling me how many standard deviations away from 0 this measure is? Or did you just do A tan H and called it a day? We just basically need better reporting and better clarity reporting. So I'll leave that part of the talk there, and then move on to the next part. Again, to me, I'm always embarrassed to actually talk about correlations, but I feel like there's just such pervasive use of it, and I feel an underappreciation of the fraught nature of composing correlations from time series, that I wanted to share that. So the next work that I'll be presenting is actually inspired by a meeting like this. Before we had the imaging section, one of the great ways that imaging statisticians had to get together were programs at SAMSI. SAMSI is the wonderful Statistics Applied Mathematics something that's in North Carolina. And it was there that I met up with Armin Schwartzman. And it was motivated in part by this problem in that in the coming of large data sets, it's no longer really that interesting to compute p-values. So when the UK Biobank is heading towards 100,000 subjects, basically there should be arbitrary power to detect any voxel. Now, of course, whether you believe that effect or not, that's a different thing. But basically, it's called the fallacy of null hypothesis testing. That basically, with enough data, you will always reject the null hypothesis. And it's similarly, even for small n's, there's this challenge of, well, when I get a cluster, well, what does that mean? We generally know if we do inference based on clusters, we say, oh, one or more voxels inside that cluster are significant. But that's really unsatisfying. And certainly, like, if there's a 2 voxel, or like, let's say there's a 10 voxel cluster, okay, that's interesting. I can interpret where that is. But if there's a 5,000 voxel cluster, you're saying all I can assert is that there is at least one significant voxel. That seems really, really weak. And so is where I was moaning to Armin about this problem, that he said, yes, I have a solution for that. He had just been in the process of publishing work related to climate change and geostatistics. For him, it was a question of, so say you have some climate temperature maps, say a map over North America of temperature change. There's variation from year to year, of course, but could you say, where is there more than 2%, where is there more than a 2 Celsius change over time? And there'll be some sample region, but you might say, well, I know there's variability. Where am I really sure that the change is greater than 2 degrees Celsius? And where am I really sure that that change is less than 2 degrees Celsius? And that's exactly what his work was. And I thought, oh, that's great. Let's do that for brain images. Let's take our images, create a set where we threshold them, call it a cluster, and then find regions that are where an inner region and an outer region, and they would have the following interpretation. So let's start in the middle, the yellow. The yellow is where we get a normal sort of clusters. We apply threshold to an image, and we'll start by talking about just bold change. And this will be an image where we're confident that this is not confident. This is the image where in the sample data there was at least 1% bold change. And this method will now produce 2 additional sets, an inner set, which are regions where we can be confident that the change is at least 1% of a true noise-free image, and an outer set where outside of that we can be confident that the true noise-free image is below that level. So, and this done with simultaneous confidence over the whole image. So how does this work? Miraculously, it's actually relatively simple. So if we just say, here's an image and we threshold it, it turns out it simply comes down to finding an upper and lower threshold. So that gives us the upper and lower set. So the upper threshold will give us the inner smaller set, and the lower threshold would be the lower set. So the whole exercise of this method is, what is the delta? What is the sort of the amount we need to blip up and blip down our threshold? And interestingly, it's actually not that complicated, and it doesn't even depend on the properties of the data everywhere in the image. It only depends on the sampling properties of the image at the boundary. So in 1D here, the boundary is just these green dots. In 2D, it will be a line. That was Armin's geospatial application. And in 3D, it will be a surface. So we only need to worry about what are the sampling properties of the residuals. So we basically need to get an estimate of the noise process on the boundary, a normalized noise process, and find the maximum distribution, and then basically finding the 95th percentile of that maximum distribution will give us the value that will tell us how to set D. So that's great. And I have to say, this was work that Armin was publishing in the Journal of the American Statistical Association. I thought, that's great. This can be like a summer project. This was now, Alex Bowring was actually an undergraduate at the time at Warwick. And I just said, hey, why don't you see if you can just bang this up? This seems really simple. Just take the JASM method and put it to work. Well, we ran into some trouble, and 2 papers later and a PhD, turns out there was a lot more to do. So here is the outline of the method, the bootstrap scheme that is in the JASA paper. Basically says, okay, so make residuals. In the simplest case, we just have data minus a sample mean. You need to standardize those by your the sample variance, and multiply by root n. So this is basically scaling them back up to behave like an instance of a normalized noise field. Those are just the standardized residuals. We now then multiply them by Rademacher. So each subject's residual gets multiplied by 1 or minus 1, and then basically make a sample mean image of that, but again rescaled to have a variance 1 and behave like a sort of the unit noise process. And it is from this that we take the maximum. We do this bootstrap over and over again. This gives us a whole distribution of the maximum, and computing the 95th percentile of this delta gives us the maximum. And there's some other multipliers I'm skipping. There's constant that I'm skipping out, but just that's the flavor of it. So we went and we applied this method And so we did some simulations. The simple simulations I'll show here are just 2D, but we also did 3D. And so we have a circle that has a magnitude and intensity of 3, and we thresholded it at 2. So it's basically there's a rim around here where it crosses 2, and so we know exactly where the true signal is. It's wherever the true noise-free signal is 2 or larger. And when we did this, we actually got these. So when we did it exactly the way in the JASA paper, we had huge overcoverage. And it turns out that there were some discretization problems. I'm going to skip over, but we look in the paper. Turns out that there's some, due to the finite voxel grid and the relatively low smoothness, we had to sort of change the way we evaluated our simulations. It didn't change the way the method would actually be used in practice, but the way that we evaluated sort of what was a success or failure in each realization had to be changed. And once we changed that, well, it went the other way. So now it was actually invalid. We're getting under coverage once we adjusted the way we assessed this. And that's led us to realize that actually there is, in the bootstrap world, it's often recommended that, so this whole method is based on the fact that this is going to be asymptotically normal, but of course this is a sample variance, and so this is something more like a T distribution. And in the bootstrap world, the common solution to that is to instead to do a T bootstrap. And the T bootstrap amounts to when you are taking the final statistic that you're interested in, normalized by the sample variance of the particular bootstrap sample that you have in hand at the time. So you're basically doing a brute force, very draconian thing. You're basically forcing each realization to have a given variance. But once we did that, we actually found that then this corrected this. So we basically went from, we're measuring we're measuring coverage sort of incorrectly. We correct the way we measure coverage, and that actually then went under coverage, and it took switching to the T bootstrap to make this then give us the nominal coverage. So those are kind of the two key things, in addition to lots of simulations that Alex added to this work to then make his neuroimage paper. When we actually put this to work on human connectome project data subjects, so this is from a working memory task where you have a 2-back task where you have to remember what was presented to you 2 items back, contrasted to a 0-back where you just press whenever you see an X or given stimuli. We will look at the regions where we can be confident that there is a 1% bold signal change or a 2% bold signal change. And here we go. So in each one of these yellow sets, these are the areas where we are confident there's at least a 1% signal change. And we get the expected areas of these parietal regions here and the posterior cingulate as expected. But the thing that's interesting to see is then when we say, well, actually, where can we be confident? And I'm sorry, and also very important is gray. So this is something I like. It really is like a confidence rule. I can be confident about where the changes are greater than something, the red, and where they're smaller. So in all of the gray, I can be confident that the change is less than 1%. If I make this more stringent, if I set the level C to be 2%, notice that some of these things actually don't have any red inside. So actually, this is my sample estimate of where in my data I saw that these voxels have a change of at least 2%. But at least as in this view, this is suggesting like, none of these, I don't have the confidence that the true noise-free mu process, the true percent pole change process is greater than 2%. I just don't have the confidence to assert that here. I do here, I do have that confidence here. And what's more, I actually have an outer region, relatively tight region where I can say, yes, I can be confident that the change is below 2%. So it's a way of moving us away from p-values to actually saying, okay, when p-values are meaningless, we're going to just have to be focusing on arbitrary thresholds. And then for those thresholds, can we characterize the spatial uncertainty in the discovered clusters? But this work was for the sample mean, the mu, and equivalently for a contrast of data. And typically, people might also want to be working in terms of Cohen's d. Now, when we first started this work, I said, well, surely people are going to want threshold T images. But I quickly corrected myself, or Armin corrected me, that it doesn't make sense to talk about T statistic. A T statistic is not a consistent estimator of anything, right? Asymptotically, T-values go to infinity when the null is not true. So they're absolutely absurd to be thinking about making confidence intervals on test statistics. That's nonsense. It is useful to talk about making confidence intervals or confidence statements about things that are estimates of a population quantity like a Cohen's d. And that was the next work that Alex took up. I'll come back to this later. Okay, so now we say, okay, actually, people often want to make inference not on just the mu, but the noise normalized mu. And again, we thought this should be so easy. Just put the methods we deployed to work on Cohen's d. No big deal. So here's a quick hint, a little mini simulation to give a hint of why this actually turned out to be more difficult than we realized. So the true mu is a ramp that goes from 0 to 10. The noise is homogeneous. It's variance 1. So the mu and the d are identical, right? So this is a noise-free d. When you look at the sample for n equals 60 subjects, you see, okay, there's some variation when you compute mu, but when you do Cohen's d, it looks very different. In fact, it seems like it's noisy over here. But remember, in expectation, I mean, the true mean should be the same because this is just this thing divided by a noisy estimate of 1. So what's going on? So you can show that Cohen's d is actually intimately related to a t statistic, and in particular, that d is 1 over square root of n times a non-central t distribution with non-centrality parameter root n, the true population Cohen's d. Okay, so how does that help us? Well, if you look at the expectation of the non-central t distribution, you see it's not just, so root n d is the non-central t distribution, and root n times this quantity here is not just that. There is a bias. So there is a bias in the mean that depends on the sample size n. Okay, but what's more is that if you look at the variance of this, you find that the variance is not constant, just dependent on the sample size, and this actually, tends towards 1. It actually has a term that depends on the true Cohen's d, or actually, I guess you call it mu, the squared Cohen's d. So this is disturbing, and this is what's going on here. What we're witnessing here is that there's increasing variance from the just due to an artifact of just the nature of the non-central t distribution. As all things equal, as the non-centrality parameter increases, the variance of the non-central t increases. Okay, so that's fine. And again, we just initially just blasted through and just tried to use the same method we'd used before. And when we did that, we basically got horrible results. And this is the sort of what we found was the problem. When you look at all the theory that makes this, that justifies this method, it's dependent on the fact that we are accurately, we have a sampling distribution that reflects the correlation in space between two voxels. So if we consider voxel S and voxel T, that covariance is determined by the variances and the correlation function ST. So that we are depending on the bootstrap that we do to actually produce samples of images that have this correlation structure, because that is our model for the raw data. So you can grind through a multivariate central limit theorem and show that the covariance matrix has these properties, and just skip to the punch here. If I'm asking what is the correlation between two different locations, what's the covariance between Cohen's d at two locations, it's not just C of ST, it's C of ST plus a quantity of CST squared plus this thing here. So it turns out that whatever our bootstrap sampling process is, it had better give us images that have this covariance structure, because the object of our inference now is a Cohen's d map, not a sample mean map. And the sample mean map was beautiful because the sample mean map had the exact same covariance structure as one single noise image, as one single image. But now our object of inference is something different. It has a different covariance structure. So whatever we do, it has to reflect that. So when we did the vanilla wild bootstrap method, which we thought was going to be really, really simple, which is just creating a Cohen's d type of residual, it didn't work, because you can show that the obvious thing to do, the obvious way of just making, just applying the same bootstrap method that we did before to the Cohen's d will give you something that has a correlation structure. If you just use the regular residuals, you get a correlation structure that reflects the original data, not the modified correlation structure that we need. So, I mean, the bootstrap is faithfully reproducing the spatial correlation structure of the data, but we needed something different. We needed this correlation structure. And this was giving our initial results. They were completely bad and weren't working. So with Fabian Telschau and others on the team, we actually came up with this approach, which is actually to say, actually, why don't we create a new type of residual? Let's take a Taylor series expansion of basically the standardized residual process, which is x over the square root of y, where you plug in the mu and sigma. And when you do this, you get the usual standardized residual minus some term. Now you can show that this is mean 0, and but crucially, when you actually work out the covariance, you can show that the covariance of these modified residuals have the covariance, the spatial covariance that you want. So that's trick number one. We had to, instead of doing bootstrap based on just regular standardized residuals, we had to come up with a new kind of Taylor series residuals, which are weird, still mean 0, but actually induce the appropriate covariance structure of a Cohen's D map. The other thing that surprised us is that it turns out that also the results were still not kind of coming into place. And we realized that part of the problem may be that not only is there a dependence on the variance of a non-central T in terms of the true Cohen's D value, but the skew of the distribution varies. So all things equal for non-central T, for non-central for a non-central parameter of 2, for different degrees of freedom, the degree of skew changes. And again, you'll usually think like, well, this is no big deal, right? With enough n, it's going to be symmetric. But what we find is that any of these things that depend on the extrema, and we do have to take the maxima over the boundary, are going to be extra sensitive to the skew. And that led us to trying to see, is there some way, the standard way that we make confidence sets is just a plus delta minus delta. That's the way the original method was working. So we're wondering, should we maybe try to change this in some way? And this still wasn't doing. Then we stumbled upon this paper by Loberscher, and this basically suggests a transformation that will make the T distribution more symmetric regardless of the non-centrality parameter. And it turns out here, it's sorry for the typo, it's the arcsine H transformation. So we actually basically produced a whole new set of machinery which says, instead of making inference directly on the Cohen's D map, we're going to make inference on a Cohen's D map that's transformed. So you take the sample Cohen's D map, you scale it by beta star, push it through the arcsine hyperbolic, and you multiply, but scale it again by a alpha star, and this gives you something that is more approximately normal for some certain annoying constants. They're easy to compute. So we now have a whole new method which basically says, instead of making inference on this confidence set, we're going to do this monotonic transformation of the Cohen's D, which is going to give us a sample quantity that is much more Gaussian-like and is going to be better behaved with respect to the bootstrap. And so this is now our modified method. We have the transform the data using, and then of course we also still need to do our fancy residuals, but we use the same principle. We use a Taylor series approximation of residuals composed from this function instead of just the usual x over square root of mu hat over sigma. And then using that, we still do the same Rademacher multipliers, flipping the sign of each subject's data. And again, using the T bootstrap. So we use the sample variance of the particular subject's data for the one particular realization of the bootstrap. And with that, we finally get the results. So keeping in mind on time here, I might skip through some of these, but we did try to do comprehensive simulations, both considering simple things, so small sphere, large sphere, multiple spheres, and taking some true data from the UK Biobank. Now, we didn't actually use UK Biobank data for the samples. We did Monte-Carlo with smooth Gaussian data, but we did take the true mean process from the UK Biobank. And the crucial thing here is that we wanted to have a representative, both heterogeneous mean and variance from the biobank. And when we did this with a small sphere, we're getting results that are, so ideally it would be right here and have exact confidence level. And we're slightly conservative, so our coverage is slightly over, but for the sort of target 95, not so bad. And similar for large sphere. and more complex spheres, and for the biobank setup. So again, we like to be right nailing it, but we're not too bad for the 95%. And of course, we would rather be slightly over, have slight over coverage than slight under coverage. So again, this is some quick summary of the results, but it was quite painstaking. We tried lots of things, and until we got this combination of both creating these new modified residuals that preserve the covariance structure of the Cohen's d process and the Labouchere arcsine H transformation to make the non-central T more symmetric, only then did our results sort of come into line as shown here. If I apply to this same data set, but now the Cohen's d maps, we can see it looks like this. And so, you know, again, it's for higher and higher Cohen's d, you can get less confidence. So for example, here, there's no place, at least as shown in this map, that I can be confident that the true noise-free Cohen's d is greater than 1.2. Whereas if I'm using a 0.8 Cohen's d threshold, I can see, yeah, okay, this region here, I can be sure it's above here. But of course, I actually have a lot of uncertainty about where Cohen's d is below 0.8 and stretching, of course, all the way down to the frontal cortex here. Now, the comparison I blew by before, I can show you again, which is, and this is prompted by the reviewers, well, what if I just done a normal t-test? You know, good old-fashioned t-test, because of course 80 subjects is not 8,000. You know, what do you get? Well, and you get bigger regions. And so this is in yellow is showing you the just using a permutation test with 80 subjects, one sample t-test. Where do I see an effect? And you might say, well, so your method's not as good. And the answer is no. This is doing something completely different. The yellow is showing you where is there evidence controlling for false positives anywhere of there being effect greater than 0. Whereas in red, we're saying, no, I want to know where is there evidence that the effect is greater than 0.5, greater than 0.8, and 1.2. And here, just showing the intersets here. So that's the difference there. Okay, so to conclude, so I packed in a lot, and after talking about the correlations and concerns with fMRI, I wanted to talk about the spatial confidence set. And it was really, the initial motivation was just trying to understand where can we say in a cluster, is there something really going on and where is it not? And these methods really do let us do that. It is consistent with a focus away from p-values and on effect sizes that I think will become more important as we all are faced with larger and larger data sets. This work is based on some really foundational work by Armin Schwartzman and his colleagues, but it turns out there was a whole lot to do to actually make these deploy and work on modest sample sizes and in 3 dimensions on in the settings described here for sample mean data and for Cohen's d. So we'll stop there. Thanks for your attention.